Hi again. So we're continuing with our t-test of a mean, essentially, a single mean hypothesis test. And we've got this stopping distance data. So we're going to, we just checked the conditions, but we need to see if this data, if the sample is nearly normal, okay? So to do that, we're going to look at the histogram and box plot. So you should have a Google Doc or Excel file, you should have a link to data. And you'll see this is the data we had on the very first page. First, I'm going to copy the title or label, and then we're going to go over to Staplet, one quantitative variable single group, because we just have one group of data. I'm going to paste that in. I can get rid of the lesson 10 part, I suppose. Either way. And then I will go ahead and paste the data right in. Control C, Control V, or you can right click. Okay, and click on Begin Analysis. Okay, it's a little harder to tell from the dot plot. We want to look at the histogram, and then also we want to add the box plot, and then we can also see our summary statistics here, so we can compare the mean and the median. Those are very close, and also let's just play around with our interval width a little bit. Interval width, or bin width, is the width of these bars. Like on Staplet, you can see there's two, well, I guess you can tell from the frequency as well. 2, 4, 3, 1. Sometimes when you change this, like if we did an interval width of 1, that just gives you a single trial, right, in each one. Just kind of try some different values here. That one looks more normal-ish, right? So the bin, it's important to realize with histograms, the bin width really does make a difference in the, can kind of make a difference in the shape. So you want to look at the mean and median and just kind of give your best assessment of whether you think this is nearly normal, okay? Now I don't see any outliers. There are no dots or stars on the box plot. So there's no outliers. It is unimodal. It's roughly symmetric. So I think we're okay to continue with this. Okay, so let's go back to the notes. This is what we did. We've got one quantitative single group. We put in our labels and our data, begin analysis, histogram, and box plot. Okay. And then, does the histogram and box plot show a nearly normal shape? What if you enter, so I just was playing around with different interval widths there. I don't think I went up to 7, but just want to make a note. Here's the original one, which I think is 5. Just to notice how, or that, the interval width or bin width can affect the shape. Okay, so another thing to be cautious of, we don't want to be misleading anyone by picking a certain interval width that doesn't match the other ones, you know. But I would say these data are nearly normal. Right, there's no outliers. It's unimodal. It's roughly symmetric. Okay, and when we look at the mean and the median, those are very close, 128.1, 128.5. Okay, great. So I think we've met our conditions, so we can go forward. So let's go ahead and do the test. Let me switch to the next page here. Okay, conduct the theoretical test and write your conclusion. Okay, now the exciting part, we get to do our test. So I'm just going to write out the hypotheses again, even though we already wrote them out. It's just nice to have them on the same page. Our null was that the mean, the population mean is 125 feet, so the actual average stopping distance. And the alternate is that we don't meet the objective. The population mean is actually greater than 125 feet. Okay, so this is not meeting the objective. Okay, strange because it's kind of like a double negative. Okay, so now we can do our t statistic. Let me get my formulas again. So we've already checked the conditions in the last one. So now we can do our t statistic. And we could put a subscript of 9 there to indicate we're doing the degrees of freedom 9. So over on the side here, I'll say degrees of freedom is 10 minus 1, always 1 less than our data, number of data values. Okay, so T9, has to do with the distribution I'm going to look it up in, right? Equals. Okay, so actually let me just write the formula since I haven't done that yet. X bar minus mu 0 over, oops, I'm too used to proportions with my square root there. S over square root of n. Okay, and now let's fill in these numbers. So I need my sample mean, which also very handy from Staplet here. That's the 128.1. feet minus our null value, right? The 0 goes with the null value of 125. And then I need our S. Our standard deviation is 4.1753. Over the square root of 10. Okay, so let's get a value for that. I'm going to use the Desmos scientific calculator. Let me just erase. Oh, that's fine. I'll leave it. Okay, so we're going to put our 128.1 minus 125. I'm going to close a parenthesis so that I get into the denominator of the whole thing. And then divide by 4.1753 divided by a square root of 10. Okay, so just double checking that matches my formatting. Yes, 2.3479. I'm going to write it down before I switch back. 2.3479. Okay, I go back to the notes here. So that is, it can be interpreted just like a z-score, right? The number of standard errors away from the null value, 2 over 2, you know, getting unusual, and then the t is a little different than the z, but we're interpreting it the same way. So this looks like it might be unusual, right? So let's go ahead and find our p-value. So the p-value is the probability of getting this t-score greater than 2.3479 because we're doing a right-tail test. And we're going to use Staplet t distribution, right? So let's go over Staplet t distribution. I think I need to make a new Staplet window for this. So I'm going to go staplet.com and go down to t distribution. You probably have a direct link for this. A p-value is an area, right? So, and our degrees of freedom are 9. And this, we're doing a right-tail test, so we're going to go to the right of a value. And that value is 2.3479. 479. Okay, and we can see it is pretty small, 2%, 0.0217. Okay, and our alpha, right, is 0.10, so it definitely is less than that. So let me write down 0.0217. So that's our p-value. And then we're comparing that is less than 0.10. So this is significant. Okay, we'll talk about the interpretation because it is an interesting interpretation. So let's write out with the p-value of 0.0217, we reject the null hypothesis. You could say it seems like it's fairly strong evidence, or you could just say evidence. There is that so I'm looking at what I wrote before and I don't like it. So let's go in terms of there is strong evidence that the tires don't meet the objective, right? And then we can interpret that further, that the tires there is strong evidence because we're rejecting the null. We're saying we're citing for the claim that they're not meeting the objective. So it's strange to have this sort of double negative situation or opposite situation. So we have strong evidence that the tires don't meet the objective, which would mean the stopping distance, the average stopping distance is more than 125 feet. Okay, so either one or both of those. Okay, so not great for the tires, is it? Let's calculate and interpret the corresponding confidence interval. Would you recommend the company adopt the new tread pattern? Why or why not? Okay, so now we get to practice our confidence interval again. And both of these together give us a more complete picture of what's going on. So let me write the formula out again. It's x bar plus or minus t star, and I'll put a 9 on it since our sample size is 10, times s over the square root of n. Okay, so I think I skipped over one part though. Calculate and interpret the corresponding confidence interval. So we do have to determine what confidence level goes with a one-tail test of 10%, right? So let me go over here. I always like to draw this out. We had a right tail test with a significance level or alpha of 0.10. So to make the sort of corresponding confidence level in here, we need to do the symmetry part where there's 10% on the other side, and that is going to leave 80 in the middle, right? Or if you prefer the formula, you can do 1 minus 2 times 0.10. Okay, I prefer to just draw it out, but you can also use the formula. Okay, so we're doing an 80% 80% confidence. That way it just matches up with our test over here. Okay, so that's important for our T star, right? So let me fill in the numbers that I know. I've got a lot just right up here, probably everything I need. 128.1, and we can see that is higher than the 125, so that's why we rejected the null. Plus or minus, we've got our T star. I'm going to leave a space for that, and I'm going to put in the 4.1753 over over square root of 10. Okay, so now let's go find our t star. So we already have our t distribution here, but we're going to switch to a value. I'm going to keep the degrees of freedom 9, and we want central area of 0.80. Okay, so that means we have to go out 1.383. And you might have noticed, because we just made that drawing, you could also do a right tail of 0.10, right? That's the same value. Isn't that interesting? So if you do central 0.8, same value, but it gives you the positive and the negative. But then you can see it corresponds to the test that we're doing. Okay, so our t star is 1.383. Okay, so now I'm going to go ahead and calculate the margin of error, plus or minus part. Let's go back over to Desmos. Okay, 128 point, oops, sorry, not doing that part yet. Just the margin of error. 1.383 times 4.1753 over square root of 10. Okay, so 1.8260. Okay, I'm going to go ahead and do the subtract and add part. And I'll put it all in the notes. 128.1 minus, oops, 1 minus 1.826 and 128.1 plus 0.826. And these are all in feet, right? So this is saying we're estimating that the true average stopping distance is between 126, 0.274, and 129, almost 130 feet. Okay, so let me write these down. Sorry, I messed that up. 126.274 to 129.926, and then of course I'm going to write feet at the end. This is 274. Okay, so does this align with our the decision we made on the test? So we said that essentially the average stopping distance was significantly more than 125, and so let's look at where 125 fits in relation to this interval. Well, the whole interval is above 125, right? Because it only goes down to 126 and something. Okay, so that agrees with rejecting the null, right? The null value is not in it, and the interval is in the direction of the claim, so that matches up. So let's summarize this here. The interval is completely above the null value of 125 feet. So that agrees with rejecting the null. Okay, and then to actually interpret the interval, we would say we are 80% confident that the true average stopping distance should have used a different color, is between, now here I'm going to round because I don't think it's necessary to have so many digits, 126.3 and 129, that would round up to 130.0 feet. That shows me that I did round it to the tenths place, but it just came out to be a 0. Okay. Okay, so far? Making sense? Now, here's another question. What would you do if there was an 11th data point of 102 feet? Okay, so I guess we would need to double check. What would that data value do? 102. So let's go back. We can just go ahead and add another data point. So I gotta put a space in there though. Okay, so it did erase everything, but now I'm going to hit begin analysis and change this to histogram. Okay, so this is an outlier on the low side, right? So would you say it's nearly normal? Probably not. But what does that do to the average? That takes you to a mean of the mean down to 125.7. So that one might not be significantly more than 125, right? So that's kind of an interesting thing. We could do a simulation in this case. It wouldn't meet the conditions for theoretical, right? Because it's not nearly normal. So let's write that down. So I would say now the sample is not nearly normal due to the low outlier. Okay, also just because you have this one outlier, do you think that, let's say maybe it would pass the test now, but do you think that is reasonable, right? Just because you got one low value and all the rest are higher. So it brings up an interesting ethical decision to make, right? So I don't think, even though it does bring it down, I don't know if I would want to trust that as far as braking distance on my car, right? Okay, but it does bring X bar down. Okay, so we could do a simulation. We could simulate. Okay. And we'll go over to stat key to do simulations in just a second. Let's look at what would you do if the 11th data point was 150 feet. So let me go back. I'm just going to click edit inputs this time. I'll have the same effect. 150, is that right? Yeah, 150. And begin analysis. Okay, now this is an outlier on the high side, right? And so this also makes it a lot more skewed. And then this would have the same conclusion though, right? That's making the case worse as far as the other, as opposed to the other one that was making the case better. Okay, so same thing here. This is not nearly normal. This gives more evidence. Of not meeting the goal. Okay, so let's go back to the 102 and simulate. So I want to show you something on, we've been going down here in Staplet to perform inference since we're already here. One thing to note about this simulate sample mean is I'm just going to show you what happens. There's a drawback to this. We can simulate the sample mean, but there's no place in Staplet to put in a null value, okay? At least that I've found. If you find it, let me know. So usually, remember, we want to simulate the null distribution. Oh, also I did the 150. I wanted to go back to the 102. I'm going to edit the inputs. Okay, I want to go back to the 102 for a second. If I do, we'll come back to simulate mean difference. So simulate sample mean, those are the only two simulations here. And so we could do this for a confidence interval, but we can't do this for a hypothesis test. Now you can see it's skewed to the left. There's no way to put in the null value, which shifts the null over. So we're going to go over to stat key. We're going to use stat key basically just for one mean, and the rest we'll use Staplet for. So let me go back to stat key main page. We want to do randomization hypothesis test for a single mean, and then we need to edit data. Okay, so this one I'm going to put stopping distance in feet, and then I need to copy my data over. Or I guess I could have copied my heading as well. Okay, and then we need to check that data has header row. And we should check n equals 10. Okay, so it's matching. Everything's matching up. And with the mean, single mean, we do have to put in our null value, just like going back to like a single proportion. You have to put in your null value. So 125 is our null value. And then it's going to use this, this sample, this variation, to simulate what the null distribution would look like. So I'm going to do 2,000 samples, and notice it's centered at the null. So that is the problem with Staplet as far as a single mean. This is the one thing for means it doesn't do, or doesn't do well. Okay, so then we were doing a right tail test, right? And oh, there's one thing I wanted to fix on the edit data. I wanted to add, well, let's just do the original one first, and then I'll add the 102. So this is the original data set. And then if we go right tail, and we put in how likely is it to get this 128.1, put in our X bar, and here we got even less of a, even smaller p-value than we did with the theoretical one. Okay, now let's put in our 102. So I'm going to go to edit data and add a 102 at the bottom. So now my n is 11, and you can see I've got it there, a lot more skewed. And now our X bar is 125.727. Okay. So that would actually pass, right? It would, we would say that they are meeting the objective, or maybe not that they are meeting it, but they're not meeting it. So this is where I think the wording is very interesting, because a company could look for strong evidence that they are meeting, right? But then they'd have to have a number less than 125. Or if they're looking for strong oh gosh, I can't even say it because it's the opposite. Because they phrased it in terms of not unless they don't meet the objective, it can be more as long as it's not significantly more than 125, right? You see how that's working? So those would be two very different tests, and if your p-value, or sorry, if your observed statistic is on the wrong side for which tail test you're doing, it's not going to pass, right? Because your p-value is going to be over half. Okay, so we did our simulation here. Simulate, I'm going to write use stat key for a single mean. And we got a p-value of, what was it? 0.425. Okay, so again, or sorry, this one would fail to reject. Fail to reject the null. Okay, so this way, if we did, use that outlier, and, we might just do that without looking at the graph and be like, oh, okay, great, they're meeting the objective. But it's not, it's really only because of that one outlier, right? So this would side for the company releasing the tires. This is in favor of the tires. Okay, so it does change the outcome there. Okay, great. Well, let me see what we're going to do in the next video. Okay, yeah. In the next video, I'll show you the theoretical calculators. Okay, I'll see you there.